The purpose of this lesson is to discuss a handful of challenges that often arise when you're using multiple linear regression to analyze real-world data. The first of these is categorical variables, or more precisely, categorical explanatory variables. If you have a categorical response variable, well, that's beyond the scope of the course. This gets into logistic regression or data mining or other things. What we're interested in, and it's a very common problem, is a categorical explanatory variable that we want to somehow use in a linear regression. So we look at techniques for transforming those. Second, there's this issue of outliers, and it's always very difficult to know what to do with outliers. Outliers matter because they very much impact the output of your regression. On the other hand, knowing what to do with them isn't a technical issue. It really comes down to understanding your data, understanding the business context, and understanding the question you're trying to answer. Third, we're going to look at collinearity, which again creates all sorts of problems for linear regression, and the solution to it, the way to get around it, is to really understand your data and understand its business context. Finally, we're going to look at non-normal distribution of residuals, which is just sort of a catch-all that you see when your regression's completed and you're looking at the residuals. You can spot problems. And basically, if your residuals, that is your error terms, are not normally distributed, if they're not random, then your errors are somehow systematic. And if your errors are systematic, you violate the assumptions of regression. And if you violate the assumptions of regression, then everything is up in the air. Your results are not legitimate. You might as well just put them in a drawer somewhere and not talk about them. You have to fix this problem before you have a valid analysis. To see why categorical variables are so important in linear regression, recall the bank celery example. So we had a variable of interest, which was celery, and we used a different variable called gender to split our employees into two samples, males and females. But what we're really interested in is the impact of gender controlling for all the other things that might be going on in people's lives that cause them to be paid more or less. Things like their education level, their prior experience. A lot of females would have had experience with childbirth, at least that's the theory, and that might have had an impact on salaries. And that wouldn't strictly be gender discrimination. It would be a little bit different. So how then can we use the power of linear regression to compare gender on one hand, which is male-female, and education and job level and years prior experience? These aren't continuous either. They're clearly categorical in this data set, but at least they're ordinal. At least they're close enough to being continuous that we can use them in linear regression. Well, what we do is we define what's called a dummy or an indicator variable, and I'm going to give this one a funny name. I'm going to call it maleness. I could have just as easily called it femaleness, but I'm going to call it maleness. So basically, someone has a maleness equal to 1 when they're a male, and when their maleness is equal to 0, then they're just the baseline, which in this case, they're female. So 0 along the maleness scale means you're a female, and a 1 along the maleness means you're a male. And we can use recoding within Microsoft Excel to give us a new column that has a 0 and a 1, which Excel and linear regression are going to treat as numerical data. This maleness variable allows us to create a scatter plot in which maleness is on the horizontal axis and celery is on the vertical axis. And what you'll see is, because people are either male or female, is that the data points either cluster on maleness equals 0, our females, or maleness equals 1, our male employees. So we have these two samples. But what's interesting is we can fit a line to this data points, and this line will minimize the error from the observed values. So what this means is the line will have a slope, and that slope will be exactly equal to what we saw before, a slope of about $8,300 difference between maleness equals 0 and femaleness equals 1. It's very easy to create a dummy variable in Microsoft Excel. All you do is make some room. In this case, I'm going to create a new column. I'll call this maleness. And then use the if function. So if this word here in F2 is literally equal to the word male, I have to get the capitalization right, then return a value of 1, otherwise return a value of 0. So that seems to work. Copy that down. And what I would probably do now is keep these values and get rid of the text. So what I mean is copy all these values, go over here, and then paste values. Now what that does is clobbers the text version and replaces it with the 0 and 1, which now means I can delete that. The reason I did that is because when I do multiple regression, I can't have split columns. All my columns for my X variable have to be together. So this is just a quick and easy way to make sure that gender is right beside my other explanatory variables, and that gender is now basically numerical. The only thing, last change I should make is indicate what my baseline is. So now it's called gender m equals 1, which reminds me that male equals 1 and female equals 0. So what do we do when the categorical variable has more than two categories or two values? It was pretty straightforward for male and female to create a dummy variable to represent maleness. But what if we have a color variable and it has, say, three values: red, green, and blue? So if we do the same trick and create a dummy variable for each value, we get the following. This works as an encoding scheme because each of the dummy variables, red, green, or blue, takes either a 1 or a 0. But as we can see, no two dummy variables take on a value of 1 at the same time. That is, these different values are mutually exclusive. The problem with this is that there's no baseline. That is, when the three dummy variables, red, green, and blue, all equal 0, that doesn't define a color. 0, 0, 0 is unknown. The thing has to be one of these three colors, assume. So what we do is we drop one of the variables. We make one of the colors the baseline, in this case blue, so that a value of red equals 0 and green equals 0 implies the baseline, or blue, in exactly the same way that a value of maleness of 0 implied female. Now we're in a position to put it all together in SAS Enterprise Guide. That is, I've created a query to remove outliers. I can create a query to recode categorical variables into dummy variables, and then I can run multiple regression with stepwise model refinement. So let's go to my query builder, modify it, and what I've done here is created a filter to only include people job grades 1, 2, 3, and 4, and exclude 5 and 6, with the rationale that those are managerial ranks and they're paid differently. The other issue here is I've got these two variables, gender and PC job, which are categorical, and we know how to recode these into continuous dummy indicator variables. So I click on add a new computed column. I simply recode the column, and I want to recode, first of all, gender. So I want to add a condition here to replace the value of female with, say, 0 or 1. Doesn't really matter. Now there's a little trick here, and what I'm doing is taking a text value, female or male, and turning it into numerical value. So I have to remember not to enclose this in quotes. My other condition is when I have male, replace that with 1, not in quotes. And those are basically all my values. If I have any other value, I'm going to deem it as missing. That's just my choice here. Then I'm going to go down and make sure I've select numeric, because that is now a numerical variable. It's no longer a text variable. On the next stage, I have to give this a name. And I'm going to call it gender, and I'm going to put a little reminder in to myself that my baseline is female and a value of 1 indicates a male. Now here is a very tricky thing. This, as the name sort of suggests, is a character format. I don't know what these character formats mean or what the syntax is, so I simply know that my 0,1 variable is not a character variable, and this will cause a problem if I leave it there, so I delete it. You have to remember to delete any kind of leftover character formats that SAS leaves in there. Here's also a good point to look at my expression to make sure it's right. It says basically when female, the gender equals female in quotation marks, then return 0, not in quotation marks, return the number 0. And similarly, when gender equals male in quotation marks, return a 1. So I hit next, finish, and there I now have a new field at the far right that's 0 or 1 based on the value of gender. We're now in a position to run a multiple regression on the bank salary data. Remember to start with the output of your query as your input data, because that's the data that has the outliers removed and the dummy variables. Go down to regression, linear regression, and we get the dialog. As before, salary is our dependent variable, and I'm going to put everything in except, of course, my categorical variables and salary as my explanatory variable. SAS obviously won't let you put salary in as a dependent variable and an explanatory variable. My model, I want this to go with backward elimination, and remember I want to see my standardized regression coefficients and my confidence intervals around my parameters. When I have that, I can hit run, and it will go away for a while, and it'll go through refining the model, and I can step through those and step through the blow-by-blow model refinement and get down to my final model. So here I see I have an R squared of about 65%. I'm explaining about 65% of the variance in salary using my model. Now my model, the refined model, is based on only 4 variables: job grade, year hired, gender, and whether or not it's a PC job. Now recall that originally we thought gender was worth about $8,300. When we did the t-test, gender was worth about $8,300. Since then, we've removed managers from the data set, and we've added dummy variables for gender and PC job so that we can use linear regression. This allows us to isolate the impact of gender, accounting for or controlling for all other things. Now, the only thing that really seems to be important here are job grade, year hired, and whether or not the person uses a personal computer. Look at the coefficient though for gender. It's gone down significantly from $8,300 to about $1,100. But we should also look at the p-value. All of a sudden the p-value is what we'd call marginally significant. It's sort of 7%. So 7 times out of 100, we would be wrong if we said there was a difference, because there would be no difference between male and females. That's a little bit on the high side. Another way to think about this is to look at the 95% confidence limits around the gender parameter. It says we can be 95% sure that the difference between males and females is somewhere between negative $100 and positive $2,400. So we tell our boss that we're pretty sure that men make more or less than women. That's not a great explanation. So it looks like when we've done the analysis this way with the outliers out and controlling for other things, that gender discrimination isn't a big problem in this bank. Now the caveat is that we removed all the managerial ranks from the data set, and if you recall when we looked at categorical data, that we had a disproportionate number of males in the managerial ranks. So depending on how you come at this, it can be complicated. Different analyses yield different outcomes. You just have to make sure you're using the right analyses and the right tools. Collinearity is a technical topic and it's sometimes difficult to understand, so I'm going to illustrate it here with an absolutely ridiculous example. So say what we're trying to do is construct a linear model to predict a person's height based on 2 explanatory variables. And the 2 explanatory variables are the person's left shoe size and right shoe size. So technically what we're trying to do is learn or parameterize a linear equation of the form y equals some intercept beta naught plus some multiplier times the right shoe size plus some multiplier times the left shoe size. And what we do in linear regression is learn these 3 parameters: beta naught, beta 1, and beta 2. It should be obvious to you that these 2 explanatory variables, left shoe size and right shoe size, are highly related to each other. In fact, for most people, they're the same number. And what we can do using a statistical tool like SAS is create what's called a scatter plot matrix. All a scatter plot matrix is a very simple way to create a scatter plot for every possible combination of variables, both the explanatory variables and the response variable. So how we read this is we look at the different columns and rows, and we can see, for example here, right shoe plotted against left shoe. And not surprisingly, there's a very strong linear correlation. We can also move over to the far right column, and we see right shoe and left shoe plotted against height. And that also provides, in both cases, a strong linear relationship. And that's actually good. That's what we expect. In fact, that's why we're using linear regression, is to learn this linear relationship between our explanatory variables, left shoe, right shoe, and the variable, the response that we're interested in, which in this case is height. But whereas it's a good thing to have a linear relationship between our explanatory variable or variables and our response variable, it is very problematic when we have a strong linear relationship between our explanatory variables. These regression results provide a pretty good example of what can happen when you have serious collinearity. First of all, if we look at the top of the output, we see that the regression model overall is very good. It's explaining 94-95% of the variance. That is, a huge amount of the variance in height is explained by a linear model that involves left shoe and right shoe sizes. And if we go down and look at right shoe, which just happens to be first, we can see that it is in fact highly significant. That is, there's almost no chance that the coefficient is equal to 0. But then we go to the left shoe and we see that it has a relatively high p-value, suggesting that there's a very good probability that the coefficient is 0. Why is this? What's going on? Well, think about how regression works. It estimates the parameter for right shoe, the slope of that line of the relationship between right shoe and height, and then holding right shoe constant, it estimates the slope of the line of left shoe. And we can actually plot this. So here we see a scatter plot showing the height that remains unexplained after controlling for right shoe. That is, incorporating the information from right shoe in the model, what's left for left shoe to explain. And it turns out almost nothing. In fact, there appears to be absolutely no relationship between left shoe and height once we've factored in the explanatory value of right shoe. This is the problem that happens in collinearity, is your parameter estimates can be pretty wonky. They're unreliable, even though the overall model is extremely good. In some cases, in fact, you'll get 0 coefficients that are significant, but a very significant model with high explained variance. That's the telltale sign of collinearity. And the solution is to take a very good hard look at the variables in your model and ask yourself, are any of them measuring the same thing, or are any of them causal? Does one cause the other? Here I can show you how to do a scatter plot matrix in SAS Enterprise Guide. So we go up to Tasks, under Graph, there's Scatter Plot Matrix. And there's a lot of choices here, but really what we want is the matrix variables. And I'm just going to select all of these, and you'll see it's only going to put in the ones that are continuous. It won't put in gender or PC job. Now here's, 10 or so variables. This is going to create a matrix. It's a little bit hard to read, but it's good just to give it a quick glance to see where problems might be. So it goes away, and here we see the scatter plot matrix, and as predicted, it's hard to read. But you do see certain fairly linear relationships. For example, over in the far corner, job grade and employee ID seem to be roughly linear, suggesting that early employees, well, who knows what it means? You'd have to sort of look at the data and figure it out. You'd have to understand something about the business. We also do see some linear relationships with salary, which is a good sign. For example, employee ID and salary tends to be a little bit linear, and job grade and salary tends to be a little bit linear. So that's not that much of a surprise. All you're doing here is getting a quick and dirty view of where you might have collinearity problems. One problem with linear regression, even in a tool like SAS, is that it never really complains that what you've done is wrong. And in fact, you have to take a fairly close look at the diagnostic output to understand whether your regression efforts are legitimate. So there's a couple different diagnostic plots that are of interest. And the critical thing, at least in practice, is the distribution of the residuals or the distribution of the errors. And SAS provides three almost identical ways of looking at the residuals, and really which one you use is up to you. So the first is a histogram. So here we see a histogram of residuals, and although it looks fairly normal, we can see a few more points on the right than we might expect given a purely normal distribution of errors. Another way, and sometimes a more useful way, is to look at the box plot. With the box plot, when you're expecting normality, the outliers are fairly obvious. So we see a few outliers here. Finally, one of the best ways, although we don't talk about it much in this course, is what's called a QQ plot, and it's fairly straightforward. It just gives you a line, and if the distribution, whatever distribution you're looking at, is normal, all the points will fall on the line. And if a lot of points fall off the line, then you don't really have a normal distribution. Now what I just said there is really important. If a lot of points fall off the line, or if a lot of points are outside of the box in your box plot, or the bars in the histogram are a little too high, you get the sense that this is very much judgment based, and in fact it is. So you have to look at your residuals and try to determine whether there's acceptable deviations from the assumption that the residuals are normally distributed. A natural question to ask if you have non-normally distributed residuals is why? And the bottom line is there can be many reasons, but one of the most common is that you don't have a linear relationship between your explanatory variables and your response variables. And this happens a surprising amount in business where you have some highly non-linear relationships. Now I said before, and one of the things you're supposed to do at the very first stages of linear regression is plot your data to ensure your explanatory variables are linearly related to your response variable. But in a multiple regression setting where you have lots of variables and maybe even some interactions, it's very hard to assess linearity on a variable by variable basis. But putting that aside, that is why you do have to look at your residual plots, because your residual plots are for the entire multivariate model. But here we give you a sense of some of the problems caused by a nonlinear relationship. I'll go back to a simple nonlinear relationship with a single explanatory variable, because otherwise I can't graph it. So here we see a relationship, and we have two problems here. One is that our response variable y is growing quite a bit quicker than our explanatory variable x. And what this means is that when we fit a line to this, and we can fit a line, it's not going to describe the data very well. A slightly more subtle problem is in the variation or the variance in the response variable y. It is actually growing, becoming wider as values of x get larger. And this is called heteroskedasticity. I hate to say that again. It's a very fancy word to describe exactly what you're seeing here. The variance in the response variable is non-constant in one or more explanatory variables. One of the things you can do when you have a non-linear relationship between your explanatory and response variables is try to transform one or both of these. So here is a graph in which I've transformed the response variable. In fact, all I've done is applied a logarithmic scale to the response variable. And what you see is a really nice result. The data points straighten out. And what this means is that I can then fit a line using linear regression to these data points. And that line will fit the data extremely well and satisfy the assumptions of linear regression and so on. And this turns out to be a very powerful technique. Do whatever you can to get the data points in a line and then fit a line using linear regression. Then you'll see afterwards we have to sort of reverse the process. In the previous slide, I applied a logarithmic scale to the response variable. And you might be wondering what's so special about a logarithmic transformation. And the short answer is nothing really. It just turns out to work well in practice and have some nice features. To illustrate this, here's a table of values, and these values are growing very large. And beside this, I show the logarithm in base 10 and the natural logarithm, which is the logarithm in base e. The bottom line is that the log of a value grows much slower than the value itself. And now, whether we use log base 10 or log base e doesn't really matter. In fact, if we plot these, if we plot the values which are growing very large on the horizontal axis, we see that the log on the vertical axis grows much slower and in a sort of analogous manner, regardless of whether we use log base 10 or log base e. It just turns out that in linear regression, log base e has a much easier interpretation. Now, working with transformed variables is conceptually a bit difficult, but in terms of practical skills and practical application, it's very straightforward. So for example, here we can use the ln formula, ln, in Excel to simply create a new column, which is the natural logarithm of celery in our bank data. Now all this means is we can use log celery as the response variable in our linear regression rather than celery. So intuitively, the equation we get is going to be ln of whatever, ln of y, equals a linear equation. Now whether our response variable is y or ln y doesn't really matter to Excel. It's just a column of numbers. Now it matters to us because if we want to get back to y, if we want to get back to celery, we have to take the anti-log, which of course gets a bit messy, but we'll see there's an easier way. Now assume we had just run a multiple regression on the bank celery data, and before we went to our boss and reported the existence or non-existence of some kind of gender discrimination, we would want to look at the diagnostic plots in SAS. So say we were looking at the box plot of our residuals and we were unhappy with these outliers up at the top. Now, two things about this data. First, this isn't too bad. Second of all, you'll recall that we actually got rid of these outliers in different ways by actually taking the outliers out of the data set. So in reality, we probably never would log transform this bank data. But let's say we're going to do it anyways. So what I'm going to do is go back to my original data set and create another query builder because I'm going to transform a variable. So to transform a variable, it's a new variable based on an old variable. So it's a calculated or a computed column. So I'm going to click on the little calculator there, and then rather than recode it or anything like that, I'm just going to use the advanced expression builder, which sounds tricky, but it's not that hard. Now, SAS, like most software, has a zillion built-in functions, and you can click on any of these or scroll down to find them. There is, not surprisingly, a log function. Now notice that in Excel log is base 10, whereas in SAS log, the word log is base E, and if you want log 10 you actually have to type log 10. It doesn't really matter. I can double click this or type it. It doesn't really matter. What the syntax here is log of some value, some numerical value. Now I know it's called celery, so I can just type this in, although if you were unsure or didn't like typing, you could always select it from a list. Anytime you double click, for example, celery, it would help build the expression. But anyways, what I have here is my variable is going to be log celery. I should give it a name. I'll call it log celery. Seems like a good name. Remember, I have to name it twice for whatever reason. Looks good, and I hit finish, and hopefully if I haven't made a typo, this log celery here that's been added to the bottom will become part of my data set. So if I scroll over, there it is. Now what I can do is run a regression using log celery. So I go to tasks, I go to regression, linear regression, and now instead of using celery as my dependent variable, I use log celery. Now for my explanatory variables, I can use whatever I have, but what I have to be very careful not to do is include celery, because obviously celery and log celery are related in a very direct and mathematically defined manner. So if I put celery into my explanatory variables, it's going to completely dominate. It's going to explain all the variants, and it's going to have zero business meaning whatsoever. So we have to be a little bit careful and think a little bit during this step. But now I can run this regression and get my results. So this isn't my best regression. Like I said, I probably wouldn't do this in practice with this particular data. But what I'm really interested in is, oops, I forgot my table. My table's not there. Modify task. I have to get around that bug, if you like. So I turn on my coefficients. Good example of how you sometimes have to do workarounds. Now I can scroll down, and when I get to the bottom, I'll find my results hidden away here somewhere. There it is. There's my final model. So my dependent variable is log celery, but now my parameter estimates are quite a bit different than they used to be. First of all, they're a lot smaller. And second of all, they can't be interpreted the way I was interpreting them before. The trick is, and the advantage of using natural logarithm, is I can now take these, instead of having to do any anti-log calculations or anything like that, I can use a handy approximation. And the approximation is express the impact or the coefficient as not a change in y, but a percentage change in y. So because this is log transformed, instead of saying each unit of education level leads to a 0.02 blah 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 increase in celery, what we say is each unit increase in education level leads to a 2% increase in celery. So it's a percentage expression. Now that's not precisely true, but it's a close enough approximation that most people use it in practice. For every increase in job grade, I'd expect a 9.8 or a 9.9% increase in celery. So although log transform complicates things a little bit, this percent interpretation makes it a lot easier to communicate your results to your coworkers.